Every time your local LLM generates text, there's a hidden data structure silently consuming gigabytes of your GPU's VRAM. At 4,000 tokens of context, it's eating 1 gigabyte. At 128K tokens, 32 gig. This single structure is the number one bottleneck for LLM inference speed and the number one cost driver for model serving. Most developers barely know it exists. It's called the KV cache, and understanding it changes how you think about every model you run. Transformer models generate text one token at a time. One word, one step. At every step, the model needs to look at every token that came before it to figure out what comes next. That's called self-attention, and it's expensive. The key insight is this: most of the work in self-attention is repeating calculations that haven't changed. The key vectors and value vectors for tokens you already generated? They're fixed. They never change. But without a cache, you'd recompute them from scratch on every single step. The KV cache stores those key and value tensors from previous steps so they're computed once and reused forever. GPT-2 called it passed back in 2019. Today it's in every serving stack, vLLM, TGI, TensorRT-LLM. It's not just an optimization. It's what makes LLM inference economically viable. Here's how attention works at a high level. Every token gets projected into three vectors: query, key, value. Query asks, what am I looking for? Key says, what do I contain? Value carries the actual information. When a new token comes in, its query needs to attend to every previous token. It compares against all the keys, scores them, then blends the values. Now here's the dumb problem. The old keys and values come from old tokens, and old tokens don't change. But without the cache, every new step recomputes them anyway. By step 100, you're doing 100 times more work than you need to. The textbook analogy works perfectly here. Without the cache, you're rereading the entire textbook for every new question. With the cache, you take notes as you go, then just look up what you need. LLM generation has two distinct phases. Most people don't think about them separately, but they behave completely differently. First is the prefill phase. Your prompt, all of it, gets processed in one parallel forward pass. This is compute bound. The GPU math units are running full speed, hammering through the prompt. All the KV pairs for the prompt tokens get computed and cached at once. Then comes the decode phase. This is where tokens come out one at a time. And this phase is memory bound. The compute units are basically idle, waiting for data to arrive from GPU memory. The bottleneck is loading the KV cache from HBM into the compute units. This is why cache optimizations matter so much. You spend most of your generation time here. Here's where it gets expensive. The KV cache grows linearly with every token you generate. But the impact compounds fast. For a typical 7 billion parameter model at 16-bit precision, 4,000 tokens of context takes about half a gigabyte of cache per request. Bump that to 32K tokens, 8 gig. 128K tokens, 32 gig. 1 million tokens? 256 gig. That's more than every consumer GPU on the market. Now multiply by batch size. Serving 64 concurrent requests at 4K context? You need 128 gigs of KV cache alone. That's almost as much as the model weights themselves for a 70 billion parameter model. The KV cache at any reasonable batch size often exceeds the model weights. That's insane, and it's the single biggest constraint on serving throughput. Not all models pay the same cache price. The biggest lever is the attention architecture itself. The original transformer uses multi-head attention. Every query head gets its own key and value pair. For a model with 32 heads, that's 32 separate KV pairs per token at every layer. At 8K hidden dimension, that's about 32 kilobytes per token. Multi-query attention flips this completely. All query heads share a single key value pair. The cache drops by a factor of 32. 32 times smaller. The quality trade-off was real for some tasks, but the cache savings were enormous. Grouped query attention splits the difference 8 kV heads shared across 32 query heads. You get a 4x cache reduction with almost no quality loss. This is why every modern model uses it: Llama 3, Mistral, Gemma. It's the sweet spot. And here's a wild trick from the GQA paper: you can convert an existing MHA checkpoint to GQA with just 5% of the original training compute. That's how Llama 2 was upgraded from Llama 1. The next lever is numerical. Store the cache in smaller numbers. Standard precision is FP16, 2 bytes per element. Drop to FP8, 1 byte per element, you have the cache. H100 GPUs do this natively, so it's basically free. There's very little quality loss. But you can go further. INT4 quantization gives 4x compression versus FP16. The Kiwi paper showed you can push to 2-bit 8x compression with tuning-free calibration. The tricky part? Keys and values have different statistical properties. Keys vary by channel, values vary by token. So smart quantization handles them differently. Per channel for keys, per token for values. Mixing these up costs you quality. Between GQA and FP8, you can shrink the cache by 8x without noticeable quality loss. That's the difference between running 4K context and 32K context on the same hardware. What if you need really long context? 1,000,000 tokens? Keeping everything isn't physically possible on consumer hardware. So you have to get selective. Research shows that about 20% of tokens contribute most of the attention mass. These are called heavy hitters, H2O for short. By keeping only those plus a small window of recent tokens, you can shrink the cache by 5x. Streaming LLM discovered something even simpler. You only need the first 4 tokens, called attention sinks, plus a sliding window of recent tokens. That's it. The model generates coherent text indefinitely on a fixed cache budget. 4 million tokens of generated output with no degradation. SnapKV does this during the prefill phase, selecting representative positions before generation even starts. 50 to 90% cache reduction with less than 1% accuracy drop. These techniques are what make long context inference practical on a single consumer GPU. Now let's talk about the system level. This is where vLLM changed everything. Traditional KV cache management allocates contiguous memory for each request. The problem? You allocate space for the worst case, maximum sequence length, but most requests are shorter. You waste 20 to 40% of your cache to fragmentation. PagedAttention applies operating system paging concepts to the KV cache. Split the cache into fixed size blocks. Allocate them on demand. A block table maps logical positions to physical blocks, just like virtual memory. The result is near zero memory waste. Blocks can even be shared across requests. If hundreds of requests share the same system prompt, they all point to the same cache blocks. Copy on write when something changes. Prefix caching takes this further. Shared prefixes, system prompts, conversation history get cached once and reused. Time to first token for cached prefixes drops to nearly zero. OpenAI, Anthropic, and Google all do this transparently now. It's why your second API call in a chat session feels faster than the first. Let's make this concrete. Here's what the KV cache means for your hardware. An RTX 4090 has 24 gigs of VRAM. With full MHA and FP16, you're looking at about 6K tokens of context before the cache eats everything. Switch to GQA and FP8, which most modern models support, and you jump to about 24K tokens. Same GPU, 4 times the context. Apple Silicon has a unique advantage here. Unified memory means the KV cache doesn't compete with dedicated GPU VRAM. The M-series chips handle much larger contexts because the cache and the model share a single pool. The bottom line? Every optimization we covered, GQA, quantization, eviction strategies, PagedAttention, is ultimately about managing one data structure. The KV cache is invisible, but it's the single biggest factor in how fast your LLM runs. Understanding it is the key to understanding inference. The KV cache is the hidden bottleneck behind every LLM you run. If you're running local models, check what your serving stack does with the cache. And drop a comment: what context length do you typically use? Are you hitting the cache wall? Subscribe for more deep dives into what makes LLMs tick.